Hello everyone. What a day today at CFD Support. It's a great day because once again we have spent enormous time and effort to deliver this new version of our engineering simulation environment, TCAE. So this is Luboš Pirkl, and I would like to welcome you to the webinar where we are going to introduce you the new version TCAE 21.9. I hope everything is working well. We are running live, so in case of any technical problems, feel free to contact us and we will gladly answer all your questions and comments. The webinar is being recorded and the recording will be made publicly available. And I think we can go ahead. So yeah, so we have prepared a lot of shiny new stuff to show. So make yourself comfortable and please follow carefully and think about what it is that you need. What it is that you need and what would you like to improve in your simulations, and tell us. At the end of the webinar, there will be a Q&A session dedicated to your questions and our answers. So feel free to ask your questions. Feel free to ask your questions anytime during the webinar. I think you can find easily the form in the menu where you can put your questions, and well, you can send us an email anytime later, and we'll be certainly happy to help anytime afterwards. Okay, I think we can really start. So I will quickly introduce the webinar speakers. I guess you won't be surprised. This will be our usual suspects. So this is me. My name is Luboš Pirkl, and my current job at CFD Support is telling the world about us. And right next door is sitting my colleague Radek Masa, who is our head engineer and senior developer, and he is also a very good friend and great father and husband, and I don't know what to say else. So Radek, can you help me?
I think it's enough. Hello to everybody. Hello to everybody. It's a pleasure to be here with you and to present you our new shiny product, because it is a big thing for us, because we are work very hard. So we are very pleased to introduce this new version to you.
Indeed.
And by the way, Luboš is also a very great person, great boss, the greatest, I think. So it's a pleasure to be here in this company.
Absolutely true. And Radek, thank you. And let's go ahead. It seems everything is working fine. So let's go ahead with our webinar. Thank you. So here's the agenda. So as usual, in the beginning, we will start with quite general information, and we will follow with the details later along the way throughout the webinar. So as usual, in the first part, there will be actually me. I will give a general introduction to what has been done and what's on the table. In the second part, it will be Radek, and he will gladly walk with you the list and comment the most significant news and capabilities in the new TCAE 21.9. And as usual, finally, in the last part, at the end of the webinar, there will be a Q&A session dedicated to your questions and our answers. So feel free to ask your questions. Feel free to ask them anytime during the webinar. Some questions will be answered right away during the webinar. The rest will be answered later via email, but you can be sure that all the relevant questions will be answered, because your feedback is so important to us. So no worries, and feel free to get in touch. Okay, so I will start with general information and go to the particular one. So CFD Support is the name of our company. It was founded in 2009. It's located in Prague, Czech Republic, and at CFD Support we deal with engineering simulations, as you know. With engineering simulations, I mean specifically CFD, FEA, FSI, and optimization, which is commonly abbreviated in the term CAE, which is, as you know, computer-aided engineering. We primarily focus on development of CAE software, which has very high added value for its users. It's definitely a high-end software, and our clients are CAE professionals who know well what they want. We are obsessed with accuracy. Accuracy is of our highest priority. And besides accuracy, we are focused on automation, repeatability, and scaling of application-tailored solutions. We don't believe in general purpose codes. We don't believe that any particular software can accurately simulate everything or that anyone can simulate anything. We only believe in sharp and focused applications. We do believe that any successful project is a result of focus, skills, experience, patience, and dedication. And yeah, this is why we are being picked anyway. And yeah, so it's about CFD support. We have very strong team of developers. We use professional tools to develop and maintain software. And I'll maybe continue to what we do. So we believe in open source, definitely. So we think open source is a great thing. And especially we believe in a combination of open source with professional support. We have mastered the process of open source integration. So in TCAE, our product, we have improved and integrated 48 open source projects, which make together with years of experience a very effective weapon. On top of that, we have invested more than 30 many years of focused code development in a team to deliver a professional simulation tool like this TCAE. So please just try to imagine how much work has been spent all across these open source projects, these 48 ones. And on top of that, we've spent 30 plus many years to deliver this TCAE. So all that makes the total value of TCAE software what it is now. It's amazing. So my point is a lot of work has been done, and we would like to share it with you. Okay, so TCAE is a simulation environment with substantial value for all the users at very reasonable costs. So that's for sure. And in TCAE, we have successfully merged the benefits of open source with the benefits of commercial codes. And I have to say that due to the open source nature, TCAE is unlimited, it's extremely flexible, and due to the commercial code nature, TCAE is it has graphical interface, it has professional technical support, it's robust, it's accurate, it's automated, it's well tested, and it's ready for the industry. It's ready for use in professional industrial projects, while open source, unfortunately, is not. So this is what you can see now. This is how the graphical interface of TCAE looks like. The user can do here pretty everything, from the simulation setup and the simulation run to the detailed post-processing of the results. And besides graphical interface, there's also batch mode available, and TCAE can run another software or be run by another software. And there are a lot of options. We will speak about them later. This is just a quick taste. Well, what's important to say, TCAE is not just one binary code. It's a system. It consists of software pieces. It consists of software modules. We call them modules, and they can be combined according to the project needs, right? So you do not need to use everything. You can just pick one or two or whatever fits to your project, and you can use it. So that's a big benefit of TCAE. So it definitely deals with CFD, FEA, FSI, and optimization. There are according to the modules that are available, and we also think like in two ways. So we have like horizontal development thinking. So we are adding new tools, new simulation plugins, more complexity. And also we have a vertical way of thinking, which is adding new applications for existing modules, new capabilities of existing modules, and new methods to the existing modules. So this is how we think in development. And practically you can use them in a way you like, because TCAE has a modular character. It means you can play a puzzle, right? You can pick any piece of software and you can plug it in, and it will very likely create an effective, very effective workflow. Because TCAE has a strong integration ability, it can fit any existing workflow possible. It's highly customizable and highly flexible. As you know, there are hundreds of CAE projects out there, either commercial, open source, or in-house, or whatever you might think. But TCAE is still here to fit in all to the system, and it can drive them. So it can run other software or be run by another software. No matter if it is in-house, commercial code, or another open source, it's TCAE is capable to cover all these. It's definitely to be run on a lot of devices, from laptops to PCs, to PC or to HPC, or it can be run easily on a cloud. So you can take it, send it to the cloud. The users have a lot of flexibility in this. TCAE is ready to load external meshes. It's ready to let's say use external FEA software. It's ready to run external optimization. It's ready to fill the machine learning libraries, or AI even, if you like. So it's definitely very flexible, and it's ready to be run. There are user-defined functions. You can write your own scripts and employ them, and TCAE is ready to take them. Yes, there are tutorials available. There are benchmarks to prove it's accurate. It works. Yeah, a couple of maybe the business model information. TCAE is a complex simulation environment, and it's extremely flexible technology. It was in the beginning, it was developed for turbo machinery field, so it's perfect with all the rotating machinery. And for the external aerodynamics, that's the best. Of course, there are a lot of other applications it can take, but it's best at turbo machinery and external aerodynamics. What's important, what people like about TCAE is there are no limitations of number of users. There are no limitations on jobs, cores, no limitations on hardware installations. There is no hardware lock. It's completely unlimited. So it's highly scalable, and the users can use their resources to the fullest, right? No matter how many employees, no matter how many engineers, no matter how many devices you have, you can use it everywhere. In Linux, in Windows, you can send it to the cloud. You can use it on cluster. Wherever you are, you have access, you can use it. So it's extremely usable, extremely scalable. It's accurate. So our number one focus is accuracy. We have proven it in many projects, and we are ready to prove it again and again and again, because it's our proud to be accurate. And maybe lastly, I would say TCAE is automated. Automation is our again very high priority. Automation brings a lot of effectivity into the system, into the engineering. Automation avoids human error. Automation is something you have to have. It's thing which is so much better than we expected in the first place. You can use TCAE as a black box, so you can put the data in, you can pull the data off. That's absolutely okay. Or you can use it as a fully sophisticated high-end software where you set all of the hundreds of parameters. It's up to you. So it's the beauty of TCAE is it's the user who decides how to use it. Okay. finally I'm getting to the new version. So we have spent like 6 months of everyday work in a team here at CFD support to deliver this. It's a really big thing. I think I can say it's the biggest release since CFD support is to the business. It's really big thing because there are a lot of new capabilities. I will not say any of them except one. There's a new simulation module for optimization, for parametric optimization. It's called TOpt. So there's new module TOpt, which enables optimization. It enables multiple runs. It enables really big things to happen, and I believe it's a really big thing. So I will allow myself to speak a little bit now about the new module TOpt, and I will hand over the presentation over to Radek, and Radek will finish all the details and say and correct my speech. So anyway, optimization motivation side. It's a really big thing. I think it's a paradigm shift. It's a new thing in engineering simulations. I mean it. It's a shift from the trial and error method to the conceptual search for the best possible, right? Let me explain. Maybe you remember what we did for last 20 years. We always like clean the model, make the mesh, set up the simulation, run the simulation, wait for the results, and look what we have, and what that's it, right? If it's okay, then it's okay. If it's not okay, then we run it again. It was a trial and error method, right? We tried something, and we've got something, but there was a lot of uncertainty involved all the time. I don't say it's now so much better, but it's gonna be definitely much better because we believe the parametric optimization helps a lot. Why? Because we believe that the world consists of parameters, right? At least the engineering world definitely consists of parameters, and engineers think in parameters. As you know, any simulation has more than 200 parameters for sure. Any simulation has more than 200 parameters. You can count in the boundary conditions and mesh properties and numerical schemes and turbulence models and everything. Plus you have another for sure hundreds of industrial product what you are going to simulate, hundreds of parameters, right, of your machines, of your product you want to simulate. So there are definitely hundreds of parameters which you can change, and you can, if you change one, then you can follow the results, right? But if you change two, then you are not sure about the effect, about the impact to the results, because there's no measure, there's no how to measure it, right? So we are definitely speaking with simulations, we are definitely speaking about the multi-dimensional problem. It's a multi-dimensional problem. The parametric space, right, is too large to navigate with random actions or one or two actions. It has to be like explored, and we have to navigate through it with sophisticated methods, right? Because as you know, a human brain, a human mind can't imagine more than 3 or 4 dimensions, maybe. If you have a good day, maybe you can do it, and that's it. But we are speaking about system which is almost endless. The complexity of the system we are speaking here about is endless. It's hundreds of parameters, right? So we are speaking about the function which has hundreds of unknowns, right? It's unbelievable how complex the world in these terms is. And due to this complexity, it has to be done by a machine, right? We have to have a method, we have to have algorithms to do that. We can't do more than 1, 2, maybe 3 dimensions, but with our manual way of work. So definitely an optimization process has to be involved. It has to be involved, it has to be automated, and it has to be taken it has to be involved in the game, because the game we play is so complex. We have no chance. The universe is so limited. to make it with our hands. So optimization is the future. That's I'm absolutely sure of, and we have to do it. So we have created this the opt module, which helps us to run multiple simulations based on parameters we prescribe. So I have just 3 quick examples for you. So number 1 is an airfoil. So we have created a workflow for an airfoil where you can just put the vertices, the nodes of an airfoil, and the workflow creates automatically mesh in construct 2D program, and the mesh is perfect and simulates. And in this task, we want to know for which angle of attack is the highest CL, right? The lift coefficient. And yeah, so the opt module can it's by the way, this is the simplest possible example. So there's one parameter, it's the angle of attack, and the opt module runs simulations, and it runs them again and again, and based on the results, it changes in a smart way, of course. It changes the angle of attack, and it's looking for the highest lift. So one application of the opt is looking for the maximal for the maximum of the optimization function, which is in this case a lift coefficient of an airfoil. It's just one application. Another application we have prepared is again very simple. It's a 3D tube. It's a pipe where it's rounded by this 180 degrees, and we have like artificially added 3 diameters at 3 locations, and the opt now is looking for the best efficiency of flow in this tube. In other words, it's the lowest pressure drop, right? So the lowest losses, lowest pressure drop in this in such case wins. And it's a combination of 3 parameters. So now it's more complicated. Now it's 3 parameters, and we are looking for the best efficiency of the best efficient flow, the lowest losses. And again, we set the simulation, run it, and the simulation, the opt runs the set of simulations, and at the end, it converges to something which is the best possible. And in the last quick example we prepared is kind of a real case, which is centrifugal fan, which has its own geometry builder, and now we have 5 parameters. So it's namely the number of blades, blade angle, blade radius, impeller width, and blade thickness. So it's basically just the impeller properties, and the opt can change them in certain range, and it can look for the best possible efficiency. So now we are really optimizing for the efficiency, and yeah, and the opt runs simulations again and again and again until it finds the best efficiency according to the let's say tolerances and limits we set. So this is definitely an example what can be done with the opt and what can't be done any other way. You can't imagine a 5-dimensional space and their combinations and their effects on the results. It's impossible. That's just think about it. It's really impossible, and it has to be an algorithm, a machine who does it. Okay, so it's quick examples. It's always looking for some extremes of functions, either highest efficiency or highest lift coefficient, or whatever you want to set, or whatever extreme you want to look for in this n-dimensional function. You can find it. Okay, so I'll go ahead. This is just a little bit about how it works. So we've been used to run standard simulations. We created the mesh, in TCAE, and then we did the CFD simulations sometimes together with FSI and FEA simulation, and it was it. Now, when the opt is involved, we have this the opt, which if it is included in the workflow, it does some decisions. For example, you can go DOE, design of experiment, or you can go purely optimize, and then you know, there are also some other decisions to make, whether you use the external optimization tool or whether you use the built-in optimization tool. Or if you go for DOE, then you decide if you know the parametric space already, or you want to explore it, find it along the way. In any case, the simulation, the new point of the parametric space is generated. The simulation is done, and then if you're converged, you can stop or go again and again and again and again until you decide you're done. Then you receive the report, and the workflow, the optimization loop stops. So all this can be discussed in detail, of course, but this is just how the diagram, how it works. That's the workflow diagram. And last couple of slides I have prepared for you is, you know, it's really complex, right? For example, this is an axial fan with two parameters. It's a flow rate and RPM, the speed of rotation. And my last information is we primarily always, or we recommend to you to do the DOE, which is the blue, which is just the traversing the parametric space. Then and the optimization starts, it's the green dots. They takes some interval which seems to be it, and then it like fires some shots to the aim, and likely finds the extreme, and then that's the result what we are looking for. This is like 3-axis plot where you can see how only with two dimensions how complex the problem can be. Of course, in the real world, this is the same case, but multiple plots where you can see the power, you can see the axial force, you can see all the other effects, the pressure, of course, and a lot of stuff where you are, what are the dependencies between parameters, each other, etc., etc. So we can say that with optimization there is much more complexity involved, but the results you obtain is another level, and this is why I think, or we think, it's a paradigm shift. Optimization is definitely the future of engineering simulations. Okay, so this was my general introduction, and now I would like to hand over the presentation to Radek and kindly ask him to follow with some details of what we have. Radek, can you please?
Yes. Can you see my screen? Can you just
Yes,
confirm?
we can. Yes.
Okay, perfect. So thank you. I will smoothly continue in the presentation of a new release. So Luboš had a general introduction what is new, and I will be more detailed in it. Not very detailed. So I think we will schedule next webinars where we introduce each module or each new feature into more detail. So this is just a showcase what is new and what can be done in a new release. So I picked up the main, let's say, the main changes, main new features which were developed. So we have here, just to be quick. So for example, in the TMesh module, the refinement regions can be now visualized. In TCFD module, we add a new type of simulation where we can now simulate a closed domain, so without the inlet and outlets. We also add a new equation of state, a Bank-Robinson for simulating real gases. We also add fixed velocity and free stream boundary condition, for example, for simulation of airfoils at a given angle of attacks more easily. We also add evaluation of the pressure coefficients and surface quantities. So now the surface quantities and more surface quantities can be exported and, for example, used for external finite element tools or directly for TFEA. We also added PBS job scheduler support for Linux systems. The really big thing is that we implemented a new, let's say, new family of heat transfer simulation, including coupled FSI, so between CFD and FEA, both ways. And the last one, the biggest thing, is a brand new module, TOpt. So I will be speaking mainly about these topics. So firstly, I will quickly introduce some of new features which are not so big but are very important and user-friendly. So first one is that we can simulate a closed domain now. So typical example could be some propellers or fans within the rooms. So the setup is pretty easy or straightforward. So you will choose the type of the simulation as a closed domain. Then you can, for example, use an implicit domain in a box shaped, and then you just need to add, instead of inlet and outlet condition, there is just a fixed condition which is necessary to properly define the mathematical problem. So you just pick one point within the domain where you know what is the pressure there. So usually some kind of reference pressure for incompressible simulation somewhere apart from an important areas, and that's it. So you can simulate, for example, I don't know, drone in a closed room, for example. The next one is a refinement regions for the T-mesh. So now you can easily add the refinement regions and you directly see them in the graphical user interface. So this is more user-friendly and you can really tune your, for example, external aerodynamic cases to have a very nice and graduated refinement from the object to follow nicely recirculation areas. And so now these regions can be visualized. In the fluid properties within the TCFD module, you can now use two equation of state, so standard for the perfect gas and the new one for the Penck-Robinson formulation of the equation of state. So more complex or more real gases can be now simulated with TCFD, mainly for kind of external aerodynamics like airflow simulation and investigation. So we have implemented free stream boundary conditions. So typically for the O-grid or C-grid meshes, you can now define any direction of the velocity, no matter what is the inlet and what is the outlet. So the free stream simulation remains the free stream boundary condition remains the same, and you can, for example, in the TOpt, you can parameterize or optimize or looking for the maximum drag coefficient or minimum drag coefficient or maximum lift coefficient via the angle of attack or via the inlet angle. So now you can use it pretty straightforward way. And for example, for simulating external aerodynamics of a car, you can set also the velocity of the wall or of the bottom part of the virtual tunnel, for example, to simulate that the car is really driving. Then a few post-processing tools. So we have some tasks to develop the pressure coefficient evaluation. So now in the runtime evaluated quantities menu, you can add the functionality to compute the pressure coefficient. You just add on which patches you would like to evaluate it, and you just add the reference velocity, which is compulsory for the formula, which is evaluating the pressure coefficient. Additional, we have developed a new surface quantities to be extracted from the simulation. This is mainly for the new heat transfer simulation. So for example, you can now extract from the CFD simulation, for example, the heat flux or heat transfer coefficient, not only on the wall, but not only on the wall, but near the wall with the given y plus. So they define the distance from the wall. You can write also the wall shear stress and other quantities. What is also new, that you can map the results to an external Abacus mesh format for example, for usage with an external tool for FEM simulations. So this is also a new feature. Well, one of the, let's say, one of the bigger project we have done and implemented within the TCAE workflow is this kind of heat transfer simulations. So what are the main features of this? So we have developed a near wall extraction from TCFD data at the given y plus. So this feature can extract the HTC coefficient or heat transfer coefficient and the reference temperature. Then we can map this reference temperature or temperature from the wall or HTC from CFD to FEA analysis. So FSI not only for the forces but also for the temperature. Therefore, there are new boundary conditions for TFEA. So there is, for example, the fixed heat flux and HTC. We basically enhance, or we we make a new setups for the boundary condition in TFEA module, so you can really combine several types of boundary conditions, including FSI from CFD, and the rest. For the rest, you can set a fixed heat flux, fixed temperature, and other temperature conditions. Then you can extract the resulting temperature on the solid. So you can extract it in the CSV format, and then this format can be loaded back into the, let's say, next CFD simulation. So you can perform a new CFD simulation with an updated temperature which you get from the solid. Yeah, so you can really have a loop to include the solid into the CFD simulation. All right, so what is the typical application? So here, for example, we have a manifold geometry, including the flow part and the solid part. So let's say in the first simulation where we don't know the ambient temperature or the temperature from the solid, so we can run a first simulation, CFD simulation, with adiabatic walls with the prescribed transient conditions, which we get from the measurement from the given engine, let's say. So this is a transient simulation, and as the output of the CFD, we get an averaged HTC coefficient and the reference temperature at the given y plus. These values or these fields are taken and set as an input for the FEA simulation. So we get all these parameters from TCFD. We can set some fixed temperature on these connections, for example, and set the constant HTC coefficient at the external wall. And then the results can be taken, exported in a CSV file, and loaded back, let's say, into the next CFD simulation. Yeah, so now we use a fixed boundary condition for the walls with a given distribution we got from the solid simulation, and let's say we can perform again the transient simulation and get the new distribution, and we can repeat let's say this loop to even more predict the better pressure distribution. So we can go again back here and let's say update update the CFD simulation again with the new temperature distribution. So how it's done in the workflow? So first in the CFD, we can enable now to save the average quantities from which, for example, the HTC coefficient is evaluated. So we can enable the write down of these average quantities. Then we can set the temperature. Yeah, but this is still the same. So we can, for example, for the first run, we can set the adiabatic wall because we don't know the distribution. And then we can export the heat transfer coefficient in TCFD by clicking here in the post-processing. So we would like to export the heat transfer coefficient at the given y plus. So this will give us directly the input for TFEA. And in the TFEA, the setup is as follows. So first we enable the fluid structure interaction. So here we compute just the heat transfer only in FEA. We set from which patch we would like to map the heat transfer coefficient. And because we are in the transient, so we will use the average quantities for FSI mapping over one cycle or two cycles of the engine, for example. Then in the boundary condition, we can add more conditions and on the solid. So for example, we have two regions with a fixed temperature. So we can pick up by some simple shapes like box, cylinders, or spheres. We can pick up the shape from the input solid geometry and set a given temperature. And then for the rest, which is also a new feature because still the, let's say, the external wall, there is no boundary condition assigned. So we can set a fixed heat transfer coefficient, for example, with a given ambient temperature and heat transfer coefficient, and we can automatically define, let's say, the complementary surface. So the surface for which no boundary condition is preset yet. So this automatically chooses the rest of the boundary, and the fixed heat transfer coefficient will be assigned. So all the boundary conditions are assigned, and we can run the TFEA simulation and get the CSV results from it. Okay. So the new implementation within the TFEA was a new, let's say, new boundary conditions and the way how to preset the boundary conditions. So there are now 4 types: fixed temperature, fixed heat flux, fixed heat transfer coefficient, or adiabatic wall. And to be more precise, there are 5 because the fifth or the first one is the FSI. Yeah. Then we have several selection modes. So you can choose which mode to use for selecting the boundary. So we have some basic shapes like box, cylinder, ball, cone. You can select the particle surface by an explicit STL file, for example, from from CFD simulation or from TMesh. You can choose also the CSV file. You can directly choose the FSI interface, so it automatically pick up the patch or interface which was set for the FSI, or the complement, so the rest surface to the already defined boundaries, or the whole boundary you can choose. And the last one, there is a feature because, for example, if you choose the box, so and the box intersects already the FSI part, so you can choose what if this boundary should rewrite the FSI or not. Yeah, so this means, okay, if I choose this boundary, it means that the fixed temperature will be prescribed everywhere, or there is also FSI options. So it means the intersected FSI area will be kept for the FSI mapping. Yeah, so basically it covers all the options to set the boundary conditions. All right, and then last thing to be able to be connected back to the TCFD, we need to check to extract the surface data from FEA. So we just click to save the temperature for this case, and we just take that we would like to save just this FSI interface to the CSV file, right? And then the new temperature field can be now computed in TCFD. So we take the CSV file, and in boundary condition we have a new boundary condition which is called fixed map temperature. We assign the given CSV file which includes the relevant data, and we can run the CFD simulation again. Yeah, so this workflow contains, let's say, the CFD simulation, get the HTC coefficient to the FEA, or send this HTC coefficient to FEA, run the FEA analysis, compute the new distribution of the temperature, which is put back to the CFD simulation, and for example, we can do another loop. Yeah, so this is now, let's say, this kind of project can be now simulated automatically, fully automatically in TCAE. All right, so this was the new feature for TFEA and mainly for FSI, which is connected to the heat transfer simulations. And now I will be speaking for a while about the new optimization module. So Lubos has already introduced all the aspects why we have developed it, because it will add powerful tool to the users to reveal the parametric space of their problems automatically without setting without running serially, let's say. So why we do that? So the fully automated workflow were somehow missing. Yeah, everything should be somehow connected to the external optimization tool, and so we would like to make an easy workflow which is connected to our modules. But also on the other way, we would like to also get the option to the user to connect the workflow to any other tool. Yeah, in-house codes, commercial tools, or simply any other software which has a API. So the workflow is fully automated. So whenever it's ready, you just hit one button and everything is done automatically. It is very easy to use with TOpt built-in features. It means you can by a click, you can extract any quantity, define any optimization function which is available, and so it is easy to use together with TMesh, TCFD, and TFEA, because all the parameters of all these modules are visible for the TOpt. So you can choose any parameter for the optimization. It also includes the Python scripting interface to modify the workflow, which gives you unlimited power. So you can connect any software which has any API. Yes, it is done by the Python scripting. So you can make a connection. You can connect each module, external tool in the one workflow and run it again, everything automatically. So the scripting interface allows to define, let's say, the custom optimization function. It can define any custom quantity to be tracked, or from which the optimization function is let's say is derived. You can define any parameter which will be communicated by an external tool and TOpt. So this altogether, it gives you really the option to connect TOpt to any external tool which has API. Well, Lubos has already speaking about this general workflow. So for those who knows already TCAE, so in the graphical user interface, you will see a new button, TOpt, and if you enable it, you will see a new item in the pipeline browser. Yeah, so there will be new TOpt button. Simply, if you run it without the TOpt options, it's run it in the standard way. You can include any module, and it is run it runs a standard workflow, or you can enable the TOpt and you can start to run loops of the standard workflows for which any parameter or any input geometry is changing, and you can do DOE or optimization. And so, and as a resulting folder structure, you will see, let's say, the same structure like without the TOpt, but it is hidden in the several runs, we'll call it. So one parameter version defines a single run, and all these runs are stored within the project file. Yeah. So it is, I think, very straightforward. This family of directories. Let's say the setup menu for the TOpt is also pretty simple. There are just several parameters to be set. So there is operation mode, so we can optimize, or we can do a simple DOE optimization, or it's not optimization but DOE loop. Yeah, just to pick up the given parameters and run them. There is a method always. Usually there is a built-in method. So there is an algorithm which is called golden section search, which I think can cover a significant proportion of projects to find out to optimize the let's say the problem. But of course we'll be adding additional algorithms, and there is also a custom, so you can connect any external tool, optimization tool, for example Dakota and others. Then there are some additional options. I will be speaking about it a little bit later. Then you said how many runs you would like to simulate maximum. You will choose the numbers or number of parameters and the given parameters. then you choose the track quantity. So what are you interested in to get from the optimization? Which quantity you would like to follow? From these quantities, you can define the optimization function, and then that's all. You can run it. So I will show the workflow or how to run it at the end of my presentation. Okay, so what is the operation mode? So as I already mentioned, there are two modes, optimize and DOE. In optimize, there is a built-in algorithm which is called golden section search. So it automatically looks for the best solution, some kind of simple algorithm which is powerful for optimization function, which has, let's say, a global extreme or local extreme, which is nicely resolved by the first series of, let's say, DOE simulations. And there is a method built in or external, so you can define a script which connects what you need. And in DOE, you can use an explicit space, which means it will give you all the keywords connected to the TMesh, TCAE, or TFEA, so you can combine any of the parameters which is available for the current TCAE run, or you can use any implicit, which is, for example, defined by a script and connected to the external tools, for example. Then there are additional options, for example, regenerate the mesh, which is pretty nice tool. So you can have, for example, loops where you have one mesh and you, for example, changing boundary condition, or you are changing revolution speed, etc. So you don't need to automatically regenerate the mesh. So there is three options. One is automatic, which should automatically decide if the mesh regeneration is necessary. But for some scenarios, this automatic tool cannot recognize if there is a need for mesh regeneration. So you can explicitly say, okay, always regenerate the mesh, or never, if you are sure. That is not needed. Then there are two custom, let's say, scripts. So custom initialization script is usually used for, let's say, generating new geometry variants. So if it's connected to the geometry builder or external parametric tool, parametric CAD, so you will just define a connection between TOpt and this external parametric tool, for example. The custom convergence script is mainly for the it is run after each optimization run, and it can be used for evaluating, let's say, a custom stopping criterion, or it can be used to connect with an external tool or user-defined formula. So typically, if you would like to use Dakota, you can import or connect this criterion from the Dakota. And max runs number is, I think, clear. It defined the maximum number of runs, so variants of parameters for the optimization. Now about the parameters. So the parameter is the value of the combination of values for given parameters. There could be many number of parameters, but the complexity of the optimization is then huge, and the parametric space is huge. But in general, you can add any number of parameters. So if you use the kind, let's say kind of parameter is a keyword, then it will give you a list of all keywords which TCAE has. So you can, for example, choose reference frame angular velocity to optimize or to run different revolution speed of any turbomachinery design, for example. The custom one creates an external parameter to be used within an external tool. So then it is easily accessible by a script and can be connected with an external tool to be set a proper value by the external tool and sent back to TOpt. So typically this parameter is loaded in an initialization script and sent to a geometry builder to create a proper variant of the geometry. Then parameter type. So for it defines the lin space or log space. It means the range of the variance of the parameter and how it is distributed. So mainly for DOE simulation, we'll just say what is the range and how many samples you need for each run or for each parameter. Or you can also set a list and explicitly write down the list of combinations of the parameter. Then there is a group ID, which defines the dependent and independent parameters. So it means dependent parameter. So if you set two parameters and you will give them a same non-zero ID, then it will be dependent. So if one is changing, then the second one is also changing with a given, let's say, to given function linearly or in a log manner. And independent means any parameter can be, any combination of the parameters is allowed. And I think the final thing to set up for the optimization are the quantities and the optimization function. So the quantity is defined, so let's say quantity like efficiency, pressure drop, I don't know, pressure at the inlet or torque or whatever, to be tracked by the TOpt. And there are also two types. So built-in gives you a list of all quantities which are evaluated by TCFD or TFEA, and the custom will give you an option to define a script which reads or compute any, let's say, any quantity what you need. The optimization function is then defined. It can be defined from the track quantities, and you can also choose if the optimization run will minimize or maximize this function. And additionally, the optimization function can be created from these quantities as a formula. Yeah, so you can, for example, combine first quantity efficiency minus, I don't know, the pressure drop. It doesn't make any sense, but it's possible. So you can combine and create your own optimization function as a function of other quantities. And there are some tolerances for trigger stopping the optimization. So generally speaking, optimization is stopped if relative or absolute tolerance is achieved, which is defined here, or if maximum number of runs is reached. Definitely it was set a little bit more above. Well, and then if you have everything preset, then the workflow is very, very straightforward. So let me quickly show how it looks. So let me go for the new version and for the tutorial. So I will get the TCFD and TOPT tutorial, and for example, I will use this parametric pipe. So let me let me open it. So the graphical user interface remains the same. It has new features connected connected to the TOPT module. So as you can see, the layout is very similar, but for example, we have now two render views. One is for a single TCFD simulation, and second one is for the TOPT browser to browse any variant which were already simulated. As you can see, the new TOPT module, the setup is here, and in the manager, there we can fill out the directory, basically the project directory in which all the TOPT runs will be stored. And if everything is preset, we can directly hit run TOPT button. Yeah, so on the background, it runs some external tool to generate the pipe mesh. I think it's just the Python script which generates the STL for the pipe. So for example, we can here, this is the first single run. So now TCFD simulation is running. So we can follow each TCFD simulation as usual. And when any run is finished, then we can browse the variants which were already simulated here in the graphical user interface, or we can also follow the HTML report. So we can automatically generate the HTML report at every given interval in minutes, or we can hit it automatically. So maybe I will a little bit wait for more runs, and meanwhile I will go back for the presentation. So the main output tool is the HTML report, also for the TOPT, where you can browse the parametric space and look how the optimization function looks like, or where we currently are with the optimization. So let me, for example, take an example of, for example, Excel fund segment, and I will open the report for the finished optimization. So in the report, you can see the simulation statistics for the optimization. So for the meshing, overall meshing time. So here, because we are running the optimization runs, or the parameters were only the angular velocity and the flow rate. So there is no need to remeshing the Excel fund every run. So this is time for just single run, because the mesh is done only at the beginning, and then it is used for the other runs. And the CFD simulation, all the CFD simulation took just, let's say, 70 minutes. Yeah, this is just an example. So the mesh is pretty small. How many processors were used? And so I will go faster. And now there is a table of the parametric space. So all the variants which were run, and what were the track quantities and their values. It also includes the simulation score, which shows you if the simulation runs properly, or if the, let's say, if the track quantity value ranges were followed. So for example, here for this combination, the tracked quantities were out of the given range. I don't know if I explicitly mention it, but for each quantity, you can set the acceptable range of the efficiency. So for example, if accept range is 0 and 1, and if from any reason, for example, if you put some non-physical boundary conditions, so the efficiency will go negative, then the optimization algorithm will automatically get rid of these results, so that it is not a relevant result for the optimization. Okay, so there are all the variants, and at the end you can follow the graphs, which shows you, for example, the optimization function within each run. And similarly, you can visualize these 3-axis graphs. Now we have just two parameters, so there is only this variant of the graph, and follow the optimization function here. Okay, and when we go back here, so if we check how it goes, so we already have 4 runs or 3 runs finished, so I can open I can generate the TOpt report. Yeah, here is the variant 1, so we can browse here through each variant. So if I click here, so this is the variant 3 which were simulated, and when the report is done, which is now, I can, let's say here, I can open the HTML view. Here in the TOpt, I will find the report, and I can visualize the report. So this is the current report for these 3 runs. These are the parameters which were already run with the value of the efficiency and optimization function, and we can follow all the quantities immediately or during the optimization. So this is really nice tool and important, let's say, output from the optimization. Okay, so I think I'm a little bit out of time, so I will stop here, and I think we can go back to Luboš. So Luboš, are you there?
Yes, I am. Thank you, Radek. It was great. Thank you very much.
Is there anything what I should emphasize?
No. It's perfect.
It
was
great.
It was exhausting. I mean, it was everything what we wanted to say, and yeah, I think we can continue in the webinar. We've showed some stuff, so now it's time to ask questions. So feel free to ask your questions. It's your time, so use it to the fullest. We'll do our best to answer your questions, or those like relevant. We think they may enrich all the other people in the audience. The very specific questions will be answered via email or the other way. So ask your questions. I'll take a look. I'm sure there are a few of them already. So I think Radek, we can start answering them.
Mm-hmm.
Well. So let's take a look. For example, I'll take a random pick. So Boyko, hello Boyko. He's our client. What type of optimization is TCAE using? Have you developed yourself, or is it open source? It's pretty simple actually. So the optimization method, the inbuilt optimization method in the current version of TCAE in the TOpt is a known method, and it's been implemented here at CFD support. So it's called golden search method, and you can find it everywhere. So you just Google golden search method, and you will see it's not very sophisticated, but it's good enough to make an optimization. And if you it's for the moment, and if you would like to have some more sophisticated method. You can employ Dakota, for example. We did it. It's easy. It's not a big deal. We have scripts for it, so just get in touch with us, and we will help you because it's been tested and it works well. And also for the next release, we will add at least one like very sophisticated optimization method for the next releases. But it's maybe it's not the most important thing we deal here with. So the method. What tool? Armin Winkler. Hello, Armin. We've met. And yeah. Great to see you again. What tool do you use to parameterize the blade of the impeller? So the geometry builder for the centrifugal fan we have shown. We made the geometry builder in Salome, so it's Salome. It's Python scripting of Salome, and it creates based on 30 parameters. It builds up the model which is ready for simulation. So it's Salome scripting. So it's this question. Boyko Tardarov is also asking if the heat transfer includes radiation. No, it does not yet. We can do it, but together with some project. So we are not going to do it like for fun. We are waiting for a collaboration with some industry for this heat transfer. I mean for this radiation heat transfer. Okay, what this is too specific. This is again not very. So Radek, can you see some question you would like to answer?
Well, I think you have go through a lot of them. Can TOpt interface with external design software such as CF Turbo? Yes, so definitely it can be connected. Yeah,
Yes.
because all the tools are ready for that. So it is made just a connection, and basically each run, the CF Turbo is run to export the STL of the current variant, and then the loop is run, and this is done for each run. So this is possible.
Absolutely, it's definitely possible, and I'm sure because we are collaborator of CF Turbo, and they're like 200 kilometers from us, and we will definitely make something together. At least you can expect some webinars about how to join everything, and it's not a big deal. It's CF Turbo is at the moment almost ready. It's almost ready to work smoothly with the opt. So that's not a big deal. It's ready to use, I would say. Okay, what else? Someone is asking whether it's open source. So that there are certainly open source parts. You have seen those 48 parts which are pure open source. The graphical interface of TCAE is proprietary. So the automation tool and the graphical interface is our code, and the rest is open source. And all the code developed based on open source is also open source. So you can there's access to all the extra code and modifications we did for open source. So you can be sure it's there. Okay. Well.
Maybe I have one. You mentioned that now it jumped. You mentioned that in TCAE user can use scripts. If I understand correct, TCAE has an API. Yes, but it's kind of API just to be connected within external tool. So let's say in the Python script, all the parameters from the TCAE and from the run is available and can be used in the both ways. So to define the parameters to send the parameters, actual parameters from the optimization to the external tool to generate and run, for example, run a CF Turbo with a new set of parameters. So CF Turbo gives us the STLs, let's say, and then in an automated way, the STLs are taken to run next run. Yeah, so basically just the script connects t-opt with external tools or do some custom tools. So there is no macro recorder because it doesn't record what TCAE do, because the script defines just a connection, yeah, or it define, let's say, new custom variable, for example.
Yeah.
But
Yep.
the usage is pretty straightforward, yeah. So I think in the one of the next webinar we will be speaking about it into detail, how to connect, yes, how to connect it into the external tool or use it in a custom way.
Yeah, and this is by the experience we know that all the cases are specific. So that it's almost impossible to make some generalizations in here. We have to discuss what you need to join with what, and then. But you can be sure that very likely it would be possible, because TCAE is ready to be run by another software, or it can run another software. So
yeah.
So we are very optimistic in all the options.
Yeah.
In here.
And basically what you preset, then you can save in the TCAE configuration file, and then basically the workflow is stored for you, and you can anytime repeat it without GUI on another computer. And so if you bring everything together, yeah, so
Sure.
basically, yeah,
The configuration file keeps all the settings and can be reproduced, copied, modified, etc. Okay, I don't see any other relevant questions. Someone is asking about the licensing and everything, so feel free to send us an email to info@cfdsupport.com, and you can be sure we will answer with all the information, send you all the info. Yes, we have academic licenses. You can use them. You can have them. We are pretty flexible also in licensing and everything. So don't worry to get in touch, and I'm sure we will find a solution. And now this is gonna be it, Radek. I think this is gonna be it. So let's continue to conclude. Okay, yeah. So yeah, I'll do that actually. So okay, so thank you for coming. Maybe yeah, this is a couple of those who already share our visions with us, who already work with us, and you're welcome. Yeah, you're welcome to join us along the way. It would be great. And yeah, I think it's time to say goodbye, Radek. What do you think?
Yeah, thank you for watching. It was a pleasure for us to introduce it during this new release, and we are very looking forward for cooperation with you, because we would like to show you how the optimization and all the TCAE can be run, and we would like to help you in your project to make everything easier. And so do not hesitate to contact us. We are really looking forward to be in touch with you. So thank you.
Okay, indeed. Yes, absolutely. That's correct. So thank you for coming. Thank you for your attention. And we are leaving for the party now, so we are in a hurry. So thank you very much for your time, and bye-bye for now.
Bye-bye.